Hi guys, let's do a review of everything we've seen so far in momentum and impulse. So we first began the unit talking about a quantity of impulse represented by the letter J and calculated by F delta T. And the way that we tried to frame this concept was that, remember when we talked about movement in general, and we said that an object at rest is going to stay at rest unless some outside force is applied to it. Or conversely, an object in motion is going to stay in motion unless there's some outside object that's going to do work on it. So we saw that early on in one-dimensional kinematics, that idea that objects need an external force in order to change their motion. So when we push on, say, a dynamics car, you are imparting an impulse to that car. You're applying a force for some amount of time delta t. Now, intuitively, you know that when you apply that force, you're going to change the velocity of the car. We also see from these calculations that the quantity of your applied force times the change in time, or the amount of time at which you apply the force, is mathematically equal to the change in the momentum of the object. So this was what we called impulse momentum theorem, and we do want to be careful about this theorem because it relates impulse to the change in momentum, not to the momentum mv. Okay, so the final equation that we had was F delta t equals m delta v. When an object started at rest, or when v initial was 0, that meant that F delta t was just equal to the final momentum of the object, since v sub I was 0. So sometimes you found impulse by calculating the force, the component of force, times the delta t, in which case you would get Newton seconds as the units. Sometimes you had to find impulse by calculating m delta v, because that is equal to F delta t. So in some problems where you have a change in velocity in a mass, you can also calculate the impulse by those numbers. And then sometimes you need to calculate impulse by looking at a graph. So anytime you see two quantities, F and delta t, being multiplied together, and you also see those quantities on the axes of your graph, you should be able to calculate the product of those two variables by finding the area under the graph. So whenever you see two things being multiplied and you also see those two things on a graph, I want you to think area under the curve. Okay, but enough about impulse, and let's get back to momentum, since that seems to be the focus of this chapter. So then we saw further in our chapter that we have something called conservation of momentum, or that the momentum of a system before a collision is equal to the momentum of a system after the collision. Now remember that the system can either be one object or it can be two objects. When it's two objects, you have to add up the momentum of each of those objects. So then you would have m1 times v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. So both the initial momentum and the final momentum are a sum of the initial condition and the final condition of each object. Now remember that in every collision, momentum is conserved. So when we started talking about types of collisions, we started to talk about kinetic energy. Now again, remember, in case you forgot, momentum is conserved. Momentum is conserved in every collision. Okay, momentum conserved, momentum conserved, momentum conserved. Now that doesn't mean kinetic energy is conserved. So there's only one type of collision, and that's an elastic collision, where kinetic energy is actually conserved. In that case, you could solve for missing variables with either conservation of momentum, m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final, or with kinetic energy by saying the initial kinetic energy is equal to the final kinetic energy, and then solving from there. For inelastic collisions, And for perfectly inelastic collisions, you cannot use conservation of kinetic energy or energy to solve those problems. You can only use conservation of momentum. Now recall that perfectly inelastic collisions are that special case where Vf is the same for both masses and they actually stick together. So looking at this table here, you can start to think about what happened in the collisions in the lab that you did. What did the elastic collisions look like? When you had both of the spring bumpers deployed and you had a head-on collision where each car, which is about equal mass, has approximately the same velocity, what did you see with the rebounding velocity? Well, you should have seen that they were about the same as the incoming velocity. So kinetic energy, as much as is possible in real life, is conserved in those collisions. Now you definitely don't see that with inelastic collisions when you start to really vary the mass and the velocity. Another way to frame this concept of conservation of momentum is that if initial momentum is equal to final momentum, then the amount of momentum that is either added or taken away from object 1 is the same amount that is conversely taken away or added from object 2. Or the change in momentum of object 1 is equal and opposite in sign to the change of momentum in object 2. So that's it, guys. I tried to keep that under 5 minutes. Looks like I went over, so apologies for that. But do take some time to watch the review videos and go over the practice test, and good luck on your test on Wednesday.